So tell me when we are, so we are streaming? Okay, so good afternoon everybody and welcome to this other Thursday here at BrIAS for this series, for a new series of seminars. So the Brussels Institute of Advanced Studies is very happy this time to host a series of seminars that are a little bit different from usual. As a matter of fact, we have invited a series of companies that will show us what they are doing in a specific field that is the field of robotics for nuclear plants. In particular, this event has been organized with the collaboration of Guerric from Nuketech that I will soon invite here to introduce us a little bit how about this day is structured. So as for the new guests that are with us, some word about the Brussels Institute for Advanced Studies. The Brussels Institute for Advanced Studies, it's an institute where we are inviting regularly guests from other countries to meet together and to spend time together in such a way that we can foster new research, new ideas and collaboration. So expect for all the new visitors a lot of questions, expect a lot of discussion, especially around the talks, and keep a mind open for new collaborations. So this said, I think I can give the word to Guerric, who will shortly introduce how this day is organized and what is the idea behind this day. So,
thank you very much, Emanuele, and thank you everyone for coming today. Those online as well. I don't know if we have many people online, but we have quite a few people physically, so that's great to see. First, a very quick word about the rationale for nuclear robotics and the reasons why Nuketech was actually very interested in taking up the invitation from the Brussels Institute for Advanced Studies to join in the organization of this seminar. A few years back, everything we talked about in the nuclear industry was how we would how we would organize the decommissioning and dismantling of nuclear facilities that were coming close to the end of their life. However, we had two major changes over the past few months. One was climate change mitigation that has been around for a while, but we came to realize that nuclear was actually a good solution to work on that. And the second one was the energy crisis, also driven by the war in Ukraine. And actually, the situation for the nuclear industry in the meantime has changed dramatically. A few months back at COP28, over 22 countries pledged to triple the global nuclear capacity by 2050. There is actually a tremendous amount of work ahead of every one of us in the nuclear industry to make it happen. If you look at the numbers in terms of manpower requirements, these are simply flabbergasting. In France, for example, when they were planning to build only 6 new reactors, the French Nuclear Association, GIFEN, stated that they would need 100,000 people to join the nuclear sector by the end of 2030, which is immense. But now they are not planning to do only 6 reactors. There are actually talks to build 40 new reactors. Where will these people come from? Actually, nobody really knows. And so one of the answers to that is robotics. So robotics automation is one way to alleviate the need for manpower in the nuclear sector, but also one really good way to make their work safer and less straining. Voilà. So that's why we need a lot of robots to be deployed in nuclear power plants in the coming years. So the day is organized, we will have 4 talks. We'll start with Philippe Loraux, who I will introduce in a minute. Then we will have Alexander Bahr from Hydromea. Then we'll have, thank you. Then we'll have a short break. Then Ludovic Dufau from Nimbl'bot. And last but not least, Alfredo Lamberti from Laborelec. And then we'll have some space for discussions and a nice demo from our colleagues of Nimbl'bot. So without further ado, let me introduce our first speaker, Philippe Loraux, engineer by training, and then a long and successful career at EDF in a wide diversity of position, but always in, if I'm not mistaken, for the most part in operations and inspection, which means that you've seen a lot of things running well, a lot of things running a little bit less well, and that allowed you to gather a lot of experience on what are the actual use cases of robotics, where it makes sense, and see also a couple of instances where it didn't work at all. And that is what you will talk about today. Thank you.
Thank you, Guerric. So I'm going to introduce myself briefly, then introduce Nuclear Valley competitiveness pool, and then we will share some humble thoughts about nuclear industry and what could robotics do in this area. So briefly, because Guerric already did it, but I've been working for EDF for 30 years, 20 years on site, mostly on PWR reactors, 2 or 3 years on Superphénix, which is a fast breeder reactor, at that time already in the dismantling phase. Mostly in operations, outages, maintenance, inspections and management. And yes, I did inspect nearly the whole French fleet. Then I spent 8 years on dismantling engineering and had the position of tender manager in dismantling solution that we were trying to sell abroad. Since 2 years, I've been working for half-time for Nuclear Valley, leading a working group on robotics, and for EDF as innovation manager. So let's talk about Nuclear Valley. So this is a French competitiveness pool of civil and defense nuclear sector. It is financed by Enterprises State Department and Army State Department, and also by the regional authorities. We have the delegation of the First Minister to select state supports to R&D and innovation projects proposed by French nuclear companies, research centers and laboratories. Nuclear Valley gathers circa 450 companies. This is now a slide about the club, which is about robotics. So this is amongst Nuclear Valley Sphere. It's a club that we launched in 2023. It gathers robotics French companies and nuclear end users. The end users can be supply chain companies or the majors. The main goal is to make solutions meet problems or the opposite. And how do we proceed? We started mapping all the solutions that were available on shelf within the companies that are members. We also did a mapping of the needs of the majors and the supply chain companies. We have meetings, workshops, events, and we try to make things go together well. In the next steps, we are going to process to audits and to try to anticipate the use of robotics in the nuclear industry, proposing some solutions to companies. So we're going to audit the process, detect what could be done in a better way, in a more effective way, in a more safer way, and we are going to propose some robotic solutions. In the nuclear industry, we have various facilities, lots of types. We have, of course, nuclear power plants. We have the prototypes. We have the fuel facilities to make fuel or to recycle fuels. We have repositories. We have waste treatment facilities. And all have roughly the same environment. Indeed, we have to face with radiations, contaminations. Regarding the material that we have concrete, stainless steel, filters, resins. We have lots of components such as pipes, valves, glove boxes, steel or concrete structures, exchanger, pumps, electric motors. We are going to act from outside, from inside, from remote, underwater, in the air. And we also have some nasty things such as asbestos, chemicals, oils, and water. We have, like in industry, hooped ladders, steep stairs, grating floors, tiny cluttered rooms, and so on. We have huge sites for most of them. So nothing actually so different from the non-nuclear industry, but radiations and contamination. So what could bring robots in nuclear industry? In the dangerous or risky tasks, robots could improve occupational safety and efficiency. The robots don't have to wear protective equipment, and those protective equipment prevent human beings from being efficient most of the time. So we could deal with asbestos, lead, high dose rate, underwater, on high temperature. When you work on high temperature environment, you have to stop every 2 hours. So it's a real time game changer. We also have chemical risks, anoxia risks, everything which won't harm any robots. For a repetitive tasks, the same, we have to frequently check all the parameters or surveillance. A robot can lower failure rate and enhance records and measure reliability. We also have tough tasks like cutting, milling, sanding, cleaning, lifting heavy weight, cleaning large surfaces, carrying. All those tasks could be held by a versatile on-site tools in opposition with what we may do currently, that is having a dedicated tool or to send the thing that has to be treated on a remote place. We also have precise and complex tasks accessed in tiny places. So robots that are precisely or could be precisely geolocated could do some dose rate mapping, some sampling, some non-destructive testing. They could also do the machining or welding of complex surfaces that a human being couldn't do. So on site, we could do complex fixing versus replacement of components or machining testing. Robotics is also a mean or a way to face the oncoming lack of resources Guerric addressed minutes ago. Indeed, it's now quite difficult to find the workforce resources we need, and we know that in the future we'll be lacking resources. So a key point could be to make job and companies more attractive, and having on board high tech like robots could do that. In some cases, we won't find the staff, and we already know that. And we know that some tasks could be easily done by robots. So robots could replace staff companies can't recruit. Robots have improved those last years. They are now versatile. They are easier every day to program and more affordable. Low code, no code are coming. It's easy to fix or to modify. It means that a company can get a robot, adapt it, use it, adapt it again, and use it for another task. This helps companies be competitive and adaptive to the high demand in nuclear area. On top of that, we have AI that will provide additional autonomous and adaptive performances and uses. I won't develop here. What could postpone or impede their use? Bad results or reliability are the consequence of not using the right robot for the right task. We have already done that in the past, trying to adapt robots from the automotive industry, trying to make them cut in the dismantling area, cut things. And it happened that the automotive robots don't withstand the vibrations, and that led to failure, numerous failures. We shouldn't overestimate nuclear environment constraints such as contamination or radiations. We have lots of products on the markets. Most of them are not hardened hardware, and it would be quite costly to adapt them to this. So the things that is very important is to really estimate the need and maybe use the on-the-shelf common market robots, and then after the task is done to get rid of it, instead of trying to over specify the needs. This is a study that we are trying to perform within Nuclear Valley members, that is mapping all the types of installation and trying to evaluate the dose rate for each area, and knowing the maximum dose rate a robot can withstand, we could estimate the part of the plants a usual common on the market robot could work in. We have already foreseen potential use cases. So those cases, for some of them, we already have some solutions, and for others, it's ongoing, or we are waiting to find some. So the first one is about waste, sorting waste automatically. So it has to deal with AI and the way robots could pick up the little parts of waste in a totally autonomous process. About security, we have huge sites to survey. Surveillance, I don't think that we would replace human beings, but it could be done in addition to what is done already by human beings. So it does already exist. We have some robots, autonomous robots, that that do the surveillance of some sites, not nuclear ones, but maybe one day. They are able of detecting intrusions, and they are also able to detect a failure in the installation by looking and analyzing the image of the plants, of the facility, and comparing it to the image of the same facility which is running in a proper way. It is also able to detect the gas leakages by using the US. So it's more than a simple guy walking around the site. It can detect lots of things. We can also have various automated inspection or controls in the facility by image analysis, comparisons, US, and all testing methods. It could also check the valve positions, oil levels, and this is very important in a running plant. Robots could also, and we have the needs of milling the contaminated cladding of components. On the cladding of component, it is the place where you can find the highly contaminated and high radiated material. So the aim is to get rid of that, to be able to send it to another plant. It will ease the transport and also the dose rates, and maybe allow the component to be free release later on. The next one is about the process of a supply chain company, and because we also have to consider all the supply chain companies. So potential automatization of the sending of, let's say, a nuclear fire damper, for example. We could also use robots to clean and map the dose rate of walls prior to be dismantled. We could also, in running plants, and automatize the room dose rate mapping that is being doing in a weekly period by the staff. We could also screen and inspect high elevation structures. This is all for me. If you have any questions, I will be happy to try to answer.
Thank you very much, Philippe.
Okay, okay.
Thank you. So thank you very much, Philippe. That was very interesting. And to me, one surprising element is you mentioned that issues and not radioactivity. While you might think that actually, if, as you mentioned, we tend to be a little bit over careful regarding the radioactive environment, which is not always necessary, actually. So my first question is, when will your study regarding the different doses in the different parts of it, the buildings will be, when will that study be available, and how much of it is actually scalable? So I guess that it will look a lot at the French park, at the French fleet, but will the conclusions be available, applicable to other fleets worldwide? So that would be a first question. And then a second question, if I may. You mentioned that, okay, we need to introduce more standard robots. Would that mean that what we can expect in the nuclear sector is mostly Boston Dynamics robots and DJI Mavic drones, super standard? Or will it be a bit more complex than that?
Okay, thank you, Guerric. So, for when? We plan to work on the mapping of NPPs first. We are going to work on PWR NPPs. So it means that the results would be relevant for the other NPP worldwide, PWRs. Then we are going to try to assess the other types of facilities I listed. So with the CEA and so on. Orano and the other companies. The idea is to have the big picture of all the nuclear industry mapping, and to see is it really a problem to send a standard robot or not? I don't know yet, but I think for except very specific ones where anyway we need really hardened robots, but I think in most cases, but we will see, at least in NPPs, I think maybe, I don't know, we'll see 60-70% of the area could be, we could work with a standard robot. I hope so. We'll see. When? I don't know. Before June, I hope, for the NPPs. standards robots. When I say standards, I mean non-hardened, and so we have on the shelf very sophisticated robots that are already working on the industry. I think we should benefit from that and use them without having a stress that they won't last because of the radiations. And have I forgotten one? No. There's one question, I see.
Another question? Yeah.
Thank you for that. And I agree with you. I think most of the places are going to be very low radiation levels, and I think the radiation is probably not going to harm the robots. I'd put it probably even higher than 60 or 70%. Where do you think it might be potentially a problem on nuclear power plants? Is it just around the core? I know, because I'm from the UK, so we have graphite reactors, and I know around the core, it's even around the core, the numbers I've seen are still relatively low.
Yeah, in the reactor building for PWR, we are most of the time we do not enter because of neutron. But I mean, for a robot, it's not such a big problem. So I was thinking about fuel facilities, or maybe when dismantling the internals. But by the way, when we do that underwater with specific machines and not robots. So I want to keep the case open, but to be honest, I think maybe more than 60%. And after that, what could be when dismantling, you will have some highly irradiated parts. And if we were to imagine to be sorting those with robots, this would be a case maybe on top of that. Yeah.
Other questions?
Well, if I may, one last question. Since you've been on the side of the operator, what is there to expect in terms of process for a company that wants to deploy a robot on a nuclear power plant in terms of approvals, certifications? It's also one element that scares people a lot. Will it take years and containers of paperwork, or is it a bit simpler?
Yeah, thank you. I should have noticed it in my presentation. We have to consider different phases or different situations. Running plants. Everything that is going in our running plants, we have to analyze and to prove that nothing could harm the installation, the facility. So this is the first point. And this, I should precise more, depending on where on the plant the robot is. If it's in the primary circuit or secondary circuit. On the secondary circuit, can be, well, so analysis must be done. In dismantling, expectations are lower because there are no more fuel in the plants. So it's not the same problem. It should be easier. But at least you must prove that the robot that doesn't belong to the equipment, to the initial equipment, won't have any harmful effects on the plants. But on the dismantling one, on the plant being dismantling, not a lot of systems are required for safety, so should be easier, much easier. And third case maybe, let's imagine we would have some robots that are doing some surveys outside the site against intrusion, or it would be an additional very positive process, which will enhance the safety. So without being harmful because it's outside the buildings. So this could be done tomorrow, I guess.
So last question from the public, and then we switch to the online.
Thank you very much. Merci. Very interesting presentation. I had just a question about the general perception within your organization of these solutions, also from the worker side or the people who are, you know, the humans in the loop of these projects. I was wondering, from your point of view, what is the general perception that you have? How do they see these systems? Do they find them helpful? What are maybe the limitations that they also see for this type of missions? Thank you.
Yes, we all have the fear that robots will replace us, and they would speak English better, they would do everything better. But so that's why when I presented the lack of resources and robots that could replace recruits, we don't have. So this is the first point. And for all the other tasks that were listed, it's non-interesting, very repetitive or risky tasks. And maybe a transition period could be that robots would do that in addition to the human being, without replacing at first what they do. First, to be sure that what they check is done in a good way and perfect way. A human being and maybe AI will help us in the next future. But when a human being does something, he does the tasks, but he is going to listen, to see, to watch, to smell, and he can detect lots of things. Vibrations and something. If we want a robot to do that, it means that the creator has to have made in or constructed or designed it on this purpose without forgetting anything. And I'm not sure it's so easy to do. So at least we will need humans. That's a good word for the end time.
So we have 4 questions from the online audience. So the first 2 questions come from Arthur Dard. So the first one is, will you also investigate existing robots, including in other industrial fields that may be relevant?
Sorry, could you repeat the beginning?
So will you also investigate existing robots, including in other industrial fields that may be relevant?
Is there any other...
Yeah.
Sorry, I don't understand the question.
Yeah, this first one.
Yes. That's why I said that radiation and contamination, which has to be we have to deal with. But all the robots that are currently on the industry are of interest. And yes, and all drones, flying ones, creeping ones, swimming ones, they all are interesting and could have a use in nuclear area.
Okay. So the second question is, what is the level of interest shown by NPP operators?
NPPs, sorry?
Nuclear power plant operators. So what is the level of interest shown by nuclear power plant operators?
We have to prove that robots are reliable first, because the first experiments we had were not so successful. Don't I think? We have to convince, and that's why within Nuclear Valley the first idea was to present all the assets of robots and to ask or to make the major think about what could you do with that tomorrow. And this may be difficult to do, so to perform. So what we now have in mind is to look carefully at a process to see what could be improved thanks to robotics, and then to present the results to the company.
Okay, so we have another question from Alexander Garus. When you speak of non-hardened robots working well, how long do you expect them to last, or what reliability do you target?
In nuclear, the reliability we expect on checking or so on, it's nearly 100%. But with the robots, we could achieve that. And if they are working in addition to what human beings are going, actually it's not a problem. So it leaves us the window open for progress. So it's not a problem. And what was the first question, sorry?
How long do you expect them to last, or what the reliability you target?
Yes, the life expectancy, I think it maybe not be a problem, because a new one will be more efficient before the previous one is dead, I think.
Okay. So the last question from the online audience is from Alessandro Sardo. Do you think there will be room for equipment development companies to enter the commissioning market, or is it already saturated?
You can find on the internet calls for tenders for lots of operations, so the market is open, especially if you are competitive and cheap.
Okay. Okay. Let's thank again the speaker, and I leave the word.
Hello. Yeah. So sorry for the very little technical break, but a bit of a last-minute shenanigans to solve. But I think we're good to go now. Yeah. Okay. Cool. So our next speaker is Alexander Bahr from Hydromea. Alexander is actually an engineer. Obtained his diploma in electrical engineering from RWTH in Aachen, if I'm not mistaken. Then went on to work for a couple of years at the Australian National University, or a couple of months. Already then on underwater autonomous vehicles, which was the start of a long career in underwater robots. He followed that by a PhD at the MIT, entitled Cooperative Navigation for Autonomous Underwater Vehicles, and a postdoc at EPFL on wireless sensors. And this whole underwater and wireless adventure led to the creation then of Hydromea, which you co-founded 9 years ago with a few colleagues, and which you are now the COO of. And yeah, we look forward to hear more about what you can do underwater. Thank you, Alexander.
Great. Thank you very much for the intro. Is that mic hot? Dip, dip. This one's good. Okay, here we go. Well, thank you very much for the introduction. So I'm going to be talking about remote inspection monitoring of submerged assets, because that's what Hydromea is about. As I was already introduced, I did a lot of research on underwater robotics, and the company Hydromea now is focusing on inspection, particularly of submerged underwater assets. So just a quick introduction of Hydromea. As already introduced, founded in 2014 by myself and my co-founder Felix Schill, who is now our CTO. We were both robotics PhDs and both worked respectively on underwater navigation myself, and he on underwater communication. Both of two issues will be very relevant. And our original focus of our company when we started was a swarm of autonomous underwater vehicles. So vehicles about 80 centimeters long, that you would deploy a whole swarm of, and they would go around and measure the water quality. Everybody thought it's a great idea. Even investors liked it. The business, seemed like a great business idea, but then it turned out, if you do look into water quality, it is a very regulatory-driven business, and even if you can get perfect data about the state of the water body, everybody finds it interesting, but unless it's scientists, nobody's going to pay for it, because nobody has to get this detailed information by law, and hence, if it's not by law, nobody will want to get it, or will wants to get it, but won't pay you for it. So we, unfortunately, had to look for something in the underwater domain that does pay money, and that happens to be inspection. And more specifically, we started off actually with inspection of confined flooded spaces. So if you imagine anything that's man-made, that's filled with water, and that typically has a lot of infrastructure inside, so it's a very complex environment to navigate in. And the first application we started off with was actually ballast water tank inspection, so the big tanks that are typically around the hull of ships that are filled with water to some extent in order to balance it out, in order to offset however much cargo is in there or not. From that application, we ventured on into water storage tanks, industrial plants, aquaculture, hydropower. So just in general, anything, again, man-made, filled with water, very complex infrastructure. The future applications that we are most looking forward to is indeed offshore wind, because there's an enormous amount of infrastructure put into the water around the world right now that right now is all new and shiny, but in the not too distant future will need inspection, and it will need inspection at a very large scale. And it is, of course, a business that has a lot lower margin than, for example, oil and gas. So the inspection will need to be much more affordable. And so robotic inspection will become very relevant there. And while we have actually not yet worked with the nuclear industry yet, we have been approached by it, because they certainly do have applications with flooded confined spaces that need inspections. So we have been approached by that, so we have put a few thoughts into it. And so I will be given a presentation with a focus on nuclear applications, but do forgive me if I don't get certain things quite right. My knowledge about that part of nuclear energy is a bit hearsay. So yes, and our company now in 2024 has grown to 33 full-time employees, the majority of which is indeed in R&D. So heavy development in everything from image recognition, robotics, mechatronics, electronics, and real-time software. And along the way in the creation of our company, a lot of products came along. Here you see the first, our AUV, that was the swarm AUV that we had devised and had created. And a lot of technology that we developed for that, like the thrusters to make it very compact, actually turned into a standalone product. And also the tower that had some optical communication inside actually became a standalone product in the form of our Luma optical modem. So these are two very successful products. I will later explain how they come into play. And when we then did decide to move into an underwater inspection robotics and creating the X-ray ROV, which is now sort of our main product, and that what, well, I'll introduce a bit, then we could just simply take our thrusters that we had already, we could take our optical communication we had already, leverage a lot of knowledge that we had in making underwater robots, and come up with an inspection robot that is not yet autonomous, but the goal is to get it there. So if I look at robotic operations in flooded nuclear facilities, the first thing that comes to my mind are the storage pools for spent rods. So I grabbed a couple of pictures off the internet of various facilities where spent rods are inside. And it was actually these kind of facilities, I think particularly the one in Sellafield, that we were at one point in time asked to take a look at. So if you now imagine you want to inspect this, and then you typically go for a so-called remotely operated vehicle. So this ROV, made by a French company called Exail, is actually specifically sold actually for that purpose to do underwater robotics. Conveniently, what they forgot to add here is that it typically comes with a long cable that is attached to it, which you need to remote control it. So if you take this robot now and you put it into one of these tanks to do some kind of inspection, well, it's to scale, it's more like this. So now you have this robot in this facility. So what kind of problems might this robot or the operator of that robot encounter. Because remember, it's not an autonomous robot. I don't think, even if autonomy were at an even higher degree than it is now, that the operators of this facility would like an autonomous robot moving around there. So the problems you may very quickly encounter when you control the robot in there is how to not get tangled. So you go through this facility, there's a lot of infrastructure there, changes all the time, and your tether getting tangled is a big risk, because if it does get tangled, somebody or something needs to go there and cut it and free your device. The other question for a robot always is, where am I? So the localization problem, and where do I need to go? The mapping problem. It's easy if you sort of see his top-down view, you can easily imagine, well, I can see the robot. But once you only see the world through the lens of the inspecting robot, it gets a lot more difficult. And the third issue which we hope we can address is, well, once it has been in there, to some degree or another, it has been contaminated. If you then do take it out, you may need to decontaminate it first, something that you would like to avoid. And so today in this presentation, I'm going to give a little bit of background of solutions that we came up with, technology that we have, that we think may address these issues that we identified there. Of course, the biggest one, or sort of our most proudest achievement, is the issue on how not to get tangled. So what you have here is, again, your bog standard ROV with a tether. And so what do we do? Well, we decided to actually cut the cord, so hence our catchy motto, by removing the tether from an ROV. So maybe a bit of a background for people that are not too familiar with under robotics. Why is it such a big deal? Well, aerial drones have literally taken off big time, and the two technologies that majorly advanced their deployment is that there's GPS, it's ubiquitous now, it's very cheap, the receivers. So any drone that flies, and as long as it flies outside, usually knows perfectly where it is with a high update rate. And for people that do any kinds of inspection jobs, you have high-speed radio. So even your standard DJI drone can get you HD video over 5, 6, 7, 10 kilometers, no problem. The moment you go underwater, both of these things instantly go away. So if that DJI drone were waterproof and you would dump it in the water, maybe for the first 5, 10 centimeters, you would still get video back, but then the video link that in air goes over 7, 10 kilometers, underwater gets you maybe centimeters. So that is a problem. Underwater, we can't do anything about a GPS. It won't get there. But you can do something about the high-speed data link, and that is where optical communication comes in. Optical communication, very simple. The idea is you convert data into blinking light, and on the other side, you convert that blinking light back to data. It's not terribly creative, but to get it actually right is it's not trivial. And that kind of optical communication is pretty much the only means through which you can get megabits per second through water wirelessly. Anything else, radio doesn't cut it. Typically what's used for underwater is acoustic communication that goes for quite some ranges, hundreds, maybe even kilometers. But usually for data rates that are in the kilobits per second at most, and of course with a high latency. So certainly not enough to get video from your robot back and low latency control into your vehicle. So because we had already developed this optical comms technology, we had a fairly easy time putting a robot together that does go without a tether. So just maybe a brief intro, and this is now actually the time where I do become a proper academic again and do cite my sources or stand on the shoulder of giants of the people who've come before me. We are, of course, not the first people who looked into free space optical communication. There were easily military experiments in the 80s already. And since then, countless academic projects that developed an optical modem underwater of some kind or another. The sad part, I mean, this is just a small subsection. This is that one that I could find, that I knew of or would find within 10 minutes on the internet. There must be dozens more. The sad bit is that except for the one that is in the very low corner, none of these ever went commercial. Everything else collected dust, which is very frustrating, and also one of the reasons where it got motivated me to actually get out of academia. So we developed an optical modem that combines the best of what other people have done before and did make it commercially available. as a standalone device, but then also as a device that lets you control our robot. And so this is like the palette we have now. You can look at data sheet stuff that's out there. Essentially devices that allow you to stream data at high speed with low latency through water. But we're not only just looking at just making a product and selling it. There are efforts to standardize optical underwater communication. So think of how Bluetooth is a standard, how Wi-Fi is a standard. There is the attempt to make a standard for any kind of wireless communication underwater. So be it the special forms of radio that exist, acoustic that exist, but also optical. And because we have this very strong academic background in underwater optical communication through my co-founder Felix Schill, we are actually leading the development of that optical underwater comm standard through an organization that's called SWIG, the Subsea Wireless Group. And in that group, you find pretty much the few people that do make optical or acoustic modems underwater, then the usual suspects, the operators that are very interested in this technology developing to a strong point, and like so the support companies that would be the intermediaries using that technology. And what we then did achieve is indeed world's first wireless ROV. So what you can see here is our X-ray vehicle, remotely controlled. And in the front it has a camera. And whatever the camera sees, the operator on the console gets an HD video live. And as you can see, it can very neatly control that. And that of course has its limitation. The optical comms do require fairly clear water. They don't necessarily require line of sight, so reflections work as well. But of course, you cannot control a vehicle that's like kilometers below you from the sea surface. But for a very specific application of these, fuel tanks, you can see how you can bring enough optical comms underwater to operate within that entire basin. So the second issue, how to avoid the decontamination. Well, there's a fairly straightforward approach to that. Is, what if your robot just never leaves the water? Then you just have to never, clean it up. And the very natural progression is that you do just give it an underwater garage in which it parks and in which it recharges. And we have actually developed this for actually an aquaculture project. The idea there's within a net, within any of these large aquaculture nets that are more and more going offshore as well, you do have a robot sitting inside that inspects the nets, inspects the fish for diseases, and the robot essentially just lives there and then comes back to the garage to recharge. So for that, we actually did develop this parking solution. The nice thing nowadays is that things like inductive charging for underwater robots, they are sort of becoming an off-the-shelf product, so that is a mostly solved problem. The other nice thing that is there is that you can offload data even faster than you could through the optical link. And so a convenient thing to do then is that you do some automatic docking. Again, there are various academic projects around the world that do sort of work on automatic docking in all sorts of fashion, be it in space, be it on land, but also be it underwater. But of course, we do have to develop our, we leverage, of course, research that has done before, but ultimately we do have to implement it in our robot. So what you see here on the left side is a mock garage, a cage that is in our pool. And what you see here is the video of the camera of the robot that looks at 4 fiducials. And from that fiducials, try to estimate its position relative to the garage. And you see that its pose estimate on the lower right corner. So if I do start it now, so here, it's not docking autonomously yet. Just my colleague is just driving it around, and just to see how well it can track its relative position with respect to the cage. Because once you do have your relative position to the cage, that is when you then start implementing any sort of auto-docking maneuvers. So that is something that is very much in development. And also sort of reflects a bit the course of our company. We did start in a fairly hardware-intense setup to developing our robot, but the side of our company that now grows fastest is certainly the software side. So anything related to image processing, mapping, the SLAM as it's so called, or just robotics and robotics software in general. That is actually the fastest growing, and that's where most of our time is invested into. And the last question, where am I and where do I need to go? So what is literally called SLAM, simultaneous localization and mapping, is key in a place like this, where the furniture, so to say, does change on a regular basis. So even if you had it all mapped out to begin with, this map doesn't help you much if stuff has been moved around. So you, as a robot moving in there, you should constantly reassess the map, localize yourself, find out what has changed. And there's an enormous body of academic work that has been done in that regard in the past 20 years. And I was involved in part of that. And we now are actually putting this, to good use to come up with auto mapping capabilities of our robot. Because ultimately, our company started with AUVs. We now went to remotely operated inspection vehicles. But the ultimate goal is, of course, to come back to an autonomous inspection drone. The industry that we work in, oil and gas, or potentially nuclear, they are, for good reasons, very conservative. So even if you had the perfect autonomous solutions, you do need certain intermediary steps to get there, to literally let you loose. So we are providing those through our tetherless solution that sort of is like a nice intermediate step till we get to the fully autonomous solution. So the whole subject of where are we going, this is something that is in even earlier development stages. We have some very nice results happening because just a lot of manpower has been put into in the last year. Unfortunately, I can not show that yet, but we hope to actually publish that soon or present it. I guess that's what you do in the company. Other things that we're working on and also very relevant, all of this inspection, all of this robotics, of course, is to the user, in a sense, meaningless, because what the user wants, they want to know how rusty is my stuff, where do I have kinks, where do I have buckling, where's the paint chipped off. So they want the so-called data. And what we also put a lot of effort in is the data processing, in this case, of the video feed. Typically, visual data is the data, inspection data that we do mostly carry out. And so for example, things like automatic corrosion mass assessment. So because you fly, you inspect an entire tank, and then you get the number 40% rust, because that is typically what comes out of these reports. So a lot of effort goes into that as well. And what should also actually not be ignored in the context of a robotic company, it's not just all software or the things that you see first and foremost. There's a lot of things that we did do. For example, just in developing our disk drive thruster, a very thin thruster. It's thin, it's hubless. So the beauty of a hubless thruster is that even if like a rope comes in, instead of wrapping itself around a shaft like a conventional thruster, it gets sucked right through. It's oilless, so it doesn't contaminate anything. And it has a lot of very neat features that make it particularly suitable for an underwater robot. And because it's so thin, your lateral control thrusters, so those that point up, don't make your vehicle very wide. Let's not forget, our competition, 95 of all other inspection robots literally look like this box. So the standard thing, you have this frame, and then you screw your stuff into the frame. This is not a hack, some laboratory hack. These are multi-million-dollar products that are actually sold to you. It's very functional, and it's not been particularly hydrodynamic. So if you do any sort of efficient inspection or like battery efficient inspection, it's not very suitable. So things like having just a flat thruster do make all the difference, because all of a sudden you get a much sleeker vehicle, and that's not just for the good looks. Reduces drag, reduces battery consumption, extends range while keeping the size the same. And of course, it ultimately makes for like a backpack-sized vehicle if you do carry it into like more remote spaces. So that sort of concludes my presentation. Just here's a bit of an outlook of where our plans are going. So of course, our plans are to go into the open water. What you see here is a floating wind turbine, the first of which are getting now deployed. This is what you essentially have to do once you run out of shallow water where you can put monopiles in. What you happen to have when you do these offshore wind that are floating, they are anchored with big chains, and these big chains will need to be inspected. Now imagine each of them has like about 3 or 6 chains, and there's going to be thousands of those out there. So you need to come up with a way more efficient inspection system than we have now. So that was one example where the vehicle operates autonomously. What we see here is you have some offshore oil infrastructure that's underwater. It's connected to the internet through a fiber to shore, and through our optical modems that are installed around the template, we essentially create like a Wi-Fi bubble in and around the template. So our inspection robot, it autonomously flies to the structure. The moment it enters the Wi-Fi bubble, you can from shore take control, because you now have a high-speed data connection that lets you see what the camera sees, and you can remotely operate it. And of course, it is a render video that you see right now, but as we speak, there are large templates that are outfitted in the North Sea now with our modems, and that will be actually having robots that autonomously approach it, and then are remote controlled from shore. So this, what you've seen there, is just a month away from reality. So thank you very much, and take your question now.
Okay. Question. Okay.
Thank you a lot. I have 2 questions. So now there is also, not in water but in air, the Li-Fi. Is your standard going in that direction? Is there agreement between the two? Because I assume that several aspects can be taken as well, because the idea is that the light bubbles will also be able to communicate with devices, because our Wi-Fi is overcrowded.
There is indeed a Li-Fi standard that is either in the making or to some parts already created. And there are now commercial products that are coming out.
Exactly.
There are, of course, niche products, because Wi-Fi actually works pretty well. And we do, of course, look at those standards while creating our own, because certain aspects can, of course, be derived from it, others not so much. But yes, we are, of course, keenly aware of it and incorporate it where we can.
Thank you. And the second question is, how, because in offshore you have also currents and so on, how you will be able to deal with that? Are you already investigating that? Because I think that is, from a control point of view, quite challenging.
Yes, so I mean, of course, to deal with current, you need 2 things. You need, of course, just the sheer horsepower to fight the current, to offset, what you pushed aside, which even more so makes the need for a hydrodynamic vehicle, because the less drag your vehicle has, the less motor power you need to stay on station. So of course we are investigating into how to make our thrusters more powerful, and of course the second part is you need to make sure that your navigation is good enough that you can station keep. The nice thing about this vehicle is it has 6 degrees of freedom, so it can stabilize itself in any axis. So that makes that part easy. But of course we do need to add more literal horsepowers and then good navigation to maintain station.
But so you think it's mostly an issue of horsepowers of the actuators instead of control issues?
The beauty of a lot of things underwater are much more complicated than anywhere else, including space. The one nice thing about underwater is there are usually not many control issues, because things happen slowly.
Okay.
So the mighty PID controller, whacks down a lot of control issues.
Okay, thank you.
Oh, thanks for the presentation. Well, going back to the nuclear, I was wondering, it's nice to have no cables going around, but one of the requirements that might come from nuclear sites is what happens if you lose your robot. You need to prove that you can remove it especially if it's in a circuit which is primary circuit, or so. Well, if you have a cable, you pull on the cable and you remove it. I don't know if there is any requirement on the fuel pool, but I guess so. You cannot just leave a robot inside the fuel pool if anything happens. So that's one of the cases that normally is included in the qualification of a robot for nuclear sites. So be able to prove that in a degraded state, the robot fails, it's dead, you can remove it. So have you thought about that? Do you think that there should be another robot then going there to pick it up? And
so yes, of course we do think about this. And it's true, the ultimate solution, if it does fail, is you send another robot that has a gripper, grips it, and then takes it back out. And of course it is a trade-off, so you gain, you have advantages through going wireless, but of course you lose your ultimate line of pulling it back when it fails. The question is how much, when your robot fails and has gone around 3 turns, you may pull that cable, but then you just pull it into some infrastructure where it gets stuck. So just because you have a tether does not mean you get it back.
That's true. It has to be proved. One of them.
But yeah, it is, of course, it is a trade-off. You gain something by reducing the risk of entanglement with the optical comms, but of course you lose a literal line of safety. So that means, of course, you need to make the benefits of the optical comms higher through great reliability than the risk of losing it, where you would rely on the tether more.
And are you working only on visual-based inspection techniques? I mean, visual, or let's say based on light, or you are also exploring other type of inspection? So underwater ultrasonic inspection.
Yeah, of course. So we do of course, because we need to make money. We do what the customer wants, and a good chunk of the inspection is indeed visual. So visual covers a lot already, particularly if you can do what we do now, where we augment that. So where it would automatically mark rust, where it automatically may mark dents and or failure points. But we also have added a UT sensor, so an ultrasonic thickness gauge. When we started, it was ballast water tank inspection, so they want visual inspection and thickness of steel. So UT is a must, so we integrated a UT sensor that also provides live A scans through the optical link, so that not only shows you what the thickness of the steel is, but if you made good contact with the steel. And we also did some tricks to make sure that our probe nicely contacts. So yes, we certainly do UT measurements. And if any other customer or any other company is out there with a sensor that we should integrate, we can do that, provided it fits onto this vehicle.
That's very interesting, I believe. But you don't need, in principle, coupling underwater. Eh? I mean, you don't need to be in contact with the probe. UT probe, it's water, so it will. The ultrasonic, you can do it without being in contact with the pipe.
No. When you do measure the thickness of a steel plate, you need to make sure that the probe properly touches that steel ultrasonic probe.
Should not. Normally, water is. Well, I will discuss it later with you, but okay.
The probe we were supposed to use has to. So.
Okay.
Customer says so.
But that's interesting.
Thank you for that. It was very interesting. So we're developing similar things with Sellafield. So and you had Sellafield's pond on one of your slides. I'm just wondering how well does it work when it starts to get turbid? Because most of the nuclear ponds are crystal clear, but the legacy ones are pretty grim.
Yeah, we certainly do know. I always thought, when I thought nuclear fuel rod pools, I thought of the crystal clear ones. But then I did learn about Sellafield and did see how dirty it can possibly get. And they were particularly interested in our localization technology, very much so because the moment it goes into the pool, that you can no longer see it from the outside. So particularly for Sellafield, they were very interested in localization. So there are means with ultrasonic to do that. That's why we actually started to heavily invest into looking into using multi-beam sonars, or at least scanning sonars. And a good chunk of our effort now goes into combining camera and multi-beam sonars to recreate these 3D maps. So that is indeed operation in murky waters, navigation in murky waters is very challenging, but also very rewarding. As for the optical comms, of course, light needs to get from A to B, and the more ambient light there is, and the more turbidity there is, the less range there is. Currently, we have a range where we say it's about, in clear water, yes, it's 50 meters. In murky waters, it's about 3 times the visibility. So if your visibility underwater, say, 2 meters, your optical comms still go like 6 meters out.
Okay. And on the comments about the tether, I don't think there would be a huge problem with putting a submersible in without a tether. At Sellafield, they have lost robots because the tether has got snagged, and then they have issues with getting it out. And I don't think it's any difference if it breaks and it's somewhere that you can't access easily. It's no different to if it's got a tether and it's snagged.
Yeah, so there's, when you do deploy one in the open ocean, then the tether is very useful because there's a good chance that you get it back by just pulling the tether. But indeed, in confined flooded spaces, the idea of pulling it back on a tether, I wouldn't count on it. Yes, but then it's boring space, no?
So thank you for your presentation. It was very interesting. I had a couple of questions. Some of them were a bit talked about as well. I want to bounce back on what he said regarding the, what was it again? Sorry, I can't remember now. Yeah, so my first question then, I was thinking more about maybe murky water where it's less clear, or maybe there might be some debris floating everywhere, and since you're relying on optics in order to communicate, I guess, would there be maybe a chance of misinformation if things would pass between the emitter and the receiver?
You would have a signal drop out. It's not that of course we check some hour packets, we do forward error correction, we do a whole lot of stuff to the data stream to make sure that it gets through across. But of course, if you block it hard enough, there will be a data outage, yes.
And so you would resend the packet, I guess, if you don't have an acknowledgement, I guess, so, yeah.
Yes, I mean, it depends on what protocol you put on top. If it's like a UDP node and it's gone, if it's a TCP-based thing, then there would be a retransmit, yes.
Okay, and my second question was basically on recovery. So what if, for example, it just dies basically, and you want to recover it? I was wondering if you actually take into consideration maybe to have a regarding buoyancy, so that it might be just more buoyant, and so that if ever it dies and it cannot control itself, it would just float back to the surface. Or if it's not one of your plans, or if you ever thought about it, it would not be interesting to have such things.
No, so the design paradigm typically is that you make these things slightly positively buoyant. So if everything else fails, it comes to the surface. Okay. Again, a valid approach in the open ocean, in confined flooded spaces, also doesn't help you. It floats to the ceiling and then it's stuck at the ceiling. Okay. So you do want to, and that is the thing about underwater robotics, like in any kind of technology, it's about reliability. So you need to make sure that the thing works. As you increase reliability, your chance of failures goes down. And again, if it does fail somewhere, apparently Sellafield doesn't care, but at other places that may care, it is not hard to send another robot in that has a gripper, grabs it, and then just pull it back. So it is a solvable issue.
And do you think it might be interesting for these types of models maybe to include some sort of active buoyancy, so maybe a ballast in order to control regarding...
There are robots that have active buoyancy control. It is a usually fairly complex mechanical device that is also very prone to failure. So you do not want to add it and you have a very good reason. And again, in a confined flooded space, it might be actually detrimental if your vehicle detects something goes wrong and then decides to increase buoyancy and then hang at the ceiling. That might be worse than just laying on the floor where you can more easily recover it. So that approach, if fail, go up, it's not a good approach in confined flooded spaces.
Okay, last short question from the audience and then we move online.
Hello. Okay. Hello. Thank you for your very interesting presentation. I want to ask about the battery or the fuel for these robots. So how long can it work in the underwater? How long for the time? And you have a 6 degree of freedom mobile robot and maybe a 2 or 3 or 4 motors for these vehicles. So it costs a lot of energy, right? So how long you have to charge it?
So actually the robot has 8 motors, huh?
Yeah.
But of course what matters for the battery is not so much how many motors you have, but how much time they run.
Yeah.
And you have it nicely ballasted, and if you had good controls, then they don't need to run very much, unless of course there is a current that you need to fight. So the beauty again of confined flooded spaces is there's typically no current inside. And when you do inspection, for example, in a nuclear fuel pool where the total distance that you travel is comparably little, it might be just a few hundred meters or even single-digit kilometers, then for that the battery charge would last you a good 4, 5, 6 hours. Mm-hmm. Of course, the moment you drop it in the North Sea, there's 2 meters per second current, it needs to constantly fight that, you know, it's gone within an hour or so.
And I have another question, because you said that the robot is inside the water in nuclear plant, in nuclear. And is there any obstacles inside under the water? Because the localization is some related to the obstacles avoidance in autonomous mobile robot, right? So do you have anything to for detect the obstacles or to not to hit the obstacles or something like this?
Yeah, so currently we already have a camera, a single camera. We did actually at one point in time have 8 cameras installed in the vehicle, 4 looking forward and then another 4 looking diagonally on the sides, just for mapping. And we are introducing now a multi-beam sonar or a pencil beam sonar. So there's a lot of obstacle detection facilities in there. To make sense, however, of all of the data is a very complex task. And yes, a good chunk of our software team is busy with nothing but exactly that problem.
Yeah, thank you.
Okay, so I think we will have time to discuss during the coffee break, and we will move for 2 questions from the online audience. So the first one is a comment from Alessandro Sardo. Congratulations, very impressive. And second question is from Arthur Dard. Do you plan to be able to take samples underwater or do any intervention?
So there's a big dividing line between inspection and intervention. So the moment you want to do any kind of intervention, you need an arm, and you need to make your vehicle bigger, and then you get into a whole other domain, which of course exists and other people successfully occupy, but we now decide that there's a lot to be done in inspection. And if you do inspection and inspection only, it allows you to keep the vehicle small. We also, of course, get occasionally asked about taking samples. I mean, yes, nothing stops us from having a little tube there that we could stab and take a sample with. But I don't know, it depends on the application, what it's useful for.
Okay, and last question is from Kentin Ramon. Are you still searching for power converter solution or are the entire design freezed?
No, I think we're good on power converters. There's not, you know, it's nothing, not terribly complicated.
Okay, so leave the...
Yeah, so I think that now we'll have a quick break. They're at the back, and we'll be back at 30 past, or that's maybe a bit too small. 35 past 40. Okay, so we have 18 minutes ahead of us. Back in 18 minutes.
I did bring a little present from the 80s, because I knew they would talk in front of the... Anybody recognize this one? Okay.
Okay, welcome to the second part. Before we continue, I want to make a bit of advertisements. It goes like that also on television at breaks. So we had a successful first forum on agriculture robots. And the next one is on the 29th of March in the AI Experience Center about sustainable robot technologies. We talk a lot about sustainable use of robots for different applications. But of course, the robot itself is also enabler or disabler of the Sustainable Development Goals. It consumes energy, it uses resources, it has sensors, communication, and so on. And during this forum, we want to especially look how we can also make the robot itself more sustainable. So that's why I would welcome you to our register for the physical attendance, of course, but also, of course, online attendance is possible. And then I think I can give the word to announce the next speaker.
Okay, so now we'll have the first talk of the second part by Ludovic Dufau from Nimbl'bot. So Ludovic is again his diploma in engineering from the École nationale supérieure d'arts et métiers in France, and then he worked for the French Commission for Atomic Energy, which became in the meantime Commission for Atomic Energy and Alternative Energy Sources, or so something like that. From what I see all across the value chain, so a bit in R&D, a bit in engineering, a bit in production, and then a bit in testing as well. So you really went through the whole process. And if I remember well, it's when you were at CA that you started developing the technology that is behind Nimbl'bot. And then almost 6 years ago, then you took the leap and you decided to create your spin-off with a couple of co-founders on this robotic arm, which you will tell us a little bit more about now. Thank you very much. And just for your information, we'll have 2 talks, and then we'll have the demo of Nimbl'bot at the back. Voilà.
Thank you for the introduction. I'm Ludovic Dufau. I'm co-founder of Nimbl'bot with Alice Lassalle. Nimbl'bot is the contraction of 2 words, nimble and robot. That means we are producing agile robots for industry. Our robot is in blue in the picture. The robot is in blue in the picture. As you can see, there is an arm here with an added joint to increase the space of work. And we also have a control unit and sensors required to pilot and control the robot. We design and manufacture a compact robotic arm to perform inspection and maintenance. Our design is based on new architecture of actuators, which are more rigid, hollow, and torsion-free. This enables us to, when we use this robot with a vector, to operate in an environment with high constraint in space or hazardous conditions. We can do this operation because of the agility of a robot and its capacity to be easily piloted. As we have discussed till now, we have a lot of questions about safety of our infrastructure, especially because we have old infrastructure and we have to make more and more control on it. We have to increase the safety of the workers, and that means we need to find solutions to make more tests in conditions that we have not defined when we launch the design of the facilities. Our technology is based on a module. Like you can see, it's 2 two bubble tubes which rotates one compared the other, and this rotation, control rotation, will climb the upper face compared to the bottom face. And to create a robot, we use several times this module. This design enables us to have a robot able to move at 360 degrees, and we have no stop. And we can have also, as soon as it's a modular system, we can design the robot with the number of modules required for the exact task we have to perform. We have also designed a lot of software to control these robots. To explain how it works, technology is composed of a module of 2 degrees of freedom. The first one is a rotation from the green tube compared to the yellow platform, and the second one is the rotation of the blue tubes with the orange platform. But it's a closed loop mechanism. That means we have an internal kinematic chain inside with a ball nut, which give the property of no torsion. And we can modelize our robot with a tilt-azimuth geometric model with 2 degrees of freedom. The space of work of this robot is a part of a sphere, and we have 2 singularities, one in the center of this area and one in the border. We have also something special. That means in the joint space area, we have 2 aspects which enable us to have the same space of work. When we use a lot of modules, we obtain a redundant mechanism. This offers opportunities for us, like obstacle avoidance. We can work in confined area, and we can share space for the 2 robots in parallel. To control these robots, we have developed algorithm based on task priority inverse kinematic control. This work has been done with the BrIAS department from University of Genoa and Central Nantes. TPIK algorithm works with actions defined with different tasks, and for each task we define a priority, and it's an optimization problem to obtain the good solution for the robots. We can also add other constraints. That means we can also optimize the shape of the robots, because we can introduce parameters for the size of the robot. For example, when we want to follow the border of a cube, we can have an optimization of the robots using 3 parameters to optimize: the dexterity, the manipulability, and the root transmission ratio. And the result we obtain in red the optimized shape of a robot, and in blue the standards, the initial value of the robots. And we can see on that picture the gain we obtain on the manipulability or the dexterity by modifying the shape of a robot to make the same task. We can also introduce other tasks like obstacle avoidance. In that case, we have introduced a task with a high priority where the robot needs to be below the blue plane. As you can see, it works for the blue robots, but for the red one, the robot crosses this plane. from for the hardware side of the robot, we have designed two products for a robot for inspection and maintenance. The robot for inspection is the NB55. It's a 60 millimeter long diameter, 80 centimeter long, and you can see on the demonstration we can introduce the robot inside the window and place the camera to make a straight line beside an obstacle. That kind of movement cannot be easily made with another kind of robot. And in the second step, we are working on a bigger robot with exactly the same design, with exactly the same algorithm. It's just the hardware, a robot more heavier to perform maintenance tasks. It's the prototype version. We are carrying on working on it. Our development is from the small robot. We are doing inspection with camera at the moment, and little by little we are implementing new features. We are implementing NDT control. We are working on gripping a gripper to pick parts with the small robots. And the bigger robot for maintenance is scheduled for 2 years later. Our robot is light compared to the other. Can be used for a mobile or fixed applications, and we can easily connect the robot with different vector and effectors, because all the development are made with ROS. And we have two others way to control the robot, specifically designed for inspection and NDT. We have a first one with a Cartesian control. As you can see on that movie, on that movie, the additional joint is a rotation. We have defined in the space a path for the end effector of the robot. The robot will go to this the beginning of this path, and after that we will follow the camera will follow the path we have programmed. The objective here is to make a check of weld on a pipe. And we have another way to control the robot. It's following path strategy. It's the demonstration we have today. We have also implemented a human interface to control the robot. At the beginning, this project is to make NDT on pipes. At the beginning, we have the camera placed on the top, close to the end effector. With this camera, we move the robot too close to the place we want to make the test. The camera is RGBD. That means we have point cloud acquisition, and it enables us to introduce the CAD model of the installation and to move the CAD model in order to make it fit with the point clouds. as soon we have sufficient localization of the point cloud, the CAD model, we can work with the CAD model to follow the path and avoid obstacles existing in the area, obstacles we cannot see with the camera. Oh, thank you.
Not yet, my microphone. Okay. Yes, we do.
Thank you very much. Thank you, Ludovic. That was really interesting. One thing that struck me is that so you do have many joints or many moving parts, and so intuitively that would increase the risk of one of them getting stuck. But then, as that crossed my head, you started talking about kinematic redundancy. Is that something you explored in one of your scenario? If one of the joints is blocked, can we still perform the task, and how efficiently can we do it?
But we have two strategies. It depends on the defect we have. If we have a communication defect or electrical defects, we have a closed loop for communication inside the robot. That means it's serial communication between all the 25 actuators. If we have a failure in between two of them, we can address the beginning with one way of the communication network and the other with the other way. It's a solution if we have a problem with communication in the robots. But sometimes if we have a mechanical problem, the redundancy enables us to obtain a robot not straight but roughly straight, and the size required to remove a robot is not so bigger than if everything is working. That means as soon as we have a problem with one actuator, we go back and we remove the robot.
Okay, there is another question from the online audience. It's about the resilience of your product. How resilient is it to radiations, it asks.
We have made some tests for the bigger one. I don't have exactly the value in head, but according to the laboratory who's made the word, we have more than 10 times the usual value we obtain for electrical components. Right. 200 gray, I think.
Okay, great, thanks. Any other questions?
Thank you for that. I know they've used snake robots in the nuclear industry. And one area they used them was for laser cutting, and for that they had. It was quite. I think it was 5 or 6 meters long, but one of the problems was that you needed 5 or 6 meters outside the area where you were deploying it, because the snake goes in and comes out, and often they're very congested spaces, and so you couldn't have that 5 or 6 meters outside the room that you're deploying the robot into. They were using tendon-driven robots, and I just wondered if yours offered any benefits over a tendon-driven robot, maybe a higher payload, so you wouldn't need such a big robot when it comes to deployment.
Yes, I think the cable-driven robots have the main problem is that all the mechanism, electronics and motors are backsides and have a very big cavity to contain them. And our choice is to place everything inside the robot. That means we can place this arm along different equipment and go very far through a small hole. Sorry.
Okay, that's good, thank you.
One more short question. Ah, okay. You were maybe. I was thinking for something else.
All right. So we saw in the video how during the operation you had to place a CAD model by hand to overlap with the point cloud. Are you looking into ways of doing that automatically? Because it feels like you can do that with an optimization problem as well, like minimizing the distance of the point clouds you get with some point clouds you generate with a CAD model. Because that seems like a possible source for like an accident.
The problem with CAD model, the reality is not exactly the CAD model we have, and we make this position of the CAD model by hand because we choose the reference, especially for the area we want to test. There is too much risk of difference between the reality and the CAD model. That means an operator is required to make a good choice at the moment.
Okay, thank you very much for your nice talk.
Thank you.
Okay. It's okay. I can. Okay, so don't forget to brace yourself for a demo of the Nimbl'bot at the end of the room, at the end of our next talk, which will be Alfredo Lamberti from Laborelec. So Alberto is an engineer as well. We've had many engineers today from the University of Napoli. After graduating, he had a little bit of an experience in the United States, as I discovered first at Penn State and then at the University of Notre Dame, which must have been a lot of fun before coming back to Brussels for more fun to do a PhD at VUB, so next door, postdoc at VUB, postdoc at UGent. And if we have a little look at your list of publications at the time, it seemed to have been mostly about structures, materials, and gradually moving to inspection, right? If I'm not mistaken. And then you switch from academia to industry to join Laborelec as NDT specialists. Yeah. So without further delay, we'll hear a little bit more about crawling robots for NDT testing then, yeah. Thank you very much.
Thank you for the introduction. I have to apologize at the beginning because today I have no voice. So I will do my best to explain what I have prepared. Yes, I didn't prepare any introduction for Laborelec, but let me just give you an overview of what Laborelec is. Laborelec is the Research and Innovation Center for the NG Group. It's one of the Research and Innovation Centers. We are based just outside Brussels, in the south of the capital region. And we have a long history in the country, more than 60 years for all the energy sector, with the very, let's say, focus on nuclear applications historically. I'm actually working in the business line nuclear for the group. Although we do innovation for the full group and also for other applications like space or very exotic, let's say, fields. So, as introduced, I will be talking a bit of our activities on robotic inspection and testing. Here it's okay. Okay. I will jump directly to the topic. Let me give you two examples of our activities. The first one is an inspection of the primary circuit in the nuclear power plant. We are talking about PWR. And the second one is for the secondary circuit. And that's what I call the Venturi case. So I will also try to address a few points which were already touched today, and I'll give you my personal, I would say, feeling. Also on the, for instance, on the amount of documents that are needed to do such type of interventions. So first, for those working in the nuclear sector, they might recognize the primary circuit. So the primary circuit is something like this. The mission that was given to us was to design a robot which was able to do the inspection of the primary loop, not a full primary loop, but part of the primary loop, to do also operations, so grinding, cleaning, radiography, NDT testing, ultrasonic, particle PT testing, and to do it in an environment which is the primary circuit. So we are talking about highly contaminated environment. The primary circuit is really the pipe that goes around the reactor. So here you see the design. That's the steam generator, the primary pump. Those were the 2 points of access for the primary circuit. Normally, from the steam generator, you have what is called the manhole. It's about, you see it here, 450 millimeters in diameter, but the primary circuit itself goes up to 800 millimeters. These are big pipes. The capability of moving a robot, which has not only to do inspection, but also to do operations in elbows like these, and also the capability to inspect and report with the precision for the NDT in the region of 1 millimeter. So here, these are more or less the summary of the requirements. In reality, to go back to the list of documents, when you work on such type of activities, this is the primary circuit, the requirements are, I would say, a small booklet of requirements to fulfill. Also on the, if you look, if I go back, can we use robot coming from non-nuclear sector to nuclear? In principle, yes. Then you need to check all the materials, because some materials are not allowed to be in contact with the primary circuit. So if, for instance, you have wheels or other part that can come into contact with the circuit, then you need to be sure that you fulfill the material checklist. Another requirement, here you see we discussed about highly contaminated and high dose rate. In reality, you will see it. The dose rate, it's not a big issue for a conventional robot, unless you come up, of course you need to teleoperate here. For humans, yes, it's a problem. You need to be away 25 meters, 30 meters away from the reactor. Then we come up with this solution, this proposition. Just to be clear, we do not produce robot, but we are more an integrator of solutions, the best available on the market. We participate in this step. The conception phase, the development, the qualification, and the trainings if it's needed. For this project, for instance, it was needed. The conception phase is really the phase where we go to the requirements, to the possible solutions on the market, nuclear, non-nuclear, everything which is available. What has to be co-designed, maybe with partners, we do it. And then there is the development phase. We also do all the development test, so the factory acceptance test of the robot, the development test that need to be done in order to fulfill the requirements of the power plant. And in this particular application, if I go back to the requirements in terms of documents, the qualification phase is huge. So here you need to account maybe 6 months of qualification for a robot like this. And then there is the training of the operators. Now, if I go back to the difference between the nuclear and non-nuclear robots, the big high dose, it's not impact the robot. The problem is that when you need to inspect and do NDT and you need to do radiography, this is the big issue. The radiographic module, the robot was conceived in order to have a main crawling system with different modules. And there was one module dedicated to radiography. Then you need to protect the robot itself, to harden the system in order to be able to withstand these type of activities, the radiographic testing. The source is so powerful that you can destroy everything. So it was designed actually for the dose given by this inspection, not for the high dose of the pipe, of the circuit. So the project is huge, so I will only concentrate on few topics today. Conception development on one module, the profilometry, laser profilometry module. So this is a bit how it looks like in the reality. So it's a module. The idea was, okay, we have one crawling system, it goes in and out, then we only remove the front part and we adapt it for the different type of inspection. The laser profilometry module was designed by me. This was my module, that's why I selected it, together with a contractor. It's a module that has 2 cameras, radial cameras, one front camera for navigation, and then there is a laser for laser triangulation. So that's a bit all the design phase. This is the list of parts and materials that has to be checked in order to be compliant. That's for one module. And I also give you a bit more the detail of the technology that in this case was used. So the idea here, the requirement was to do the inspection of the welds. And the welds are done automatically with the robot. Then after you weld, you need to inspect the root penetration. If there is any lack of fusion, then we had to grind the root penetration and we had to re-inspect the pipe and the weld in order to be sure that we didn't grind too much. We didn't remove too much material because the wall thickness is defined. So we had to check that. How we did it with this module, laser profilometry. So the laser profilometry is a laser triangulation techniques. So if you have a laser beam like this, you can measure normally in this range. So here you have the schematic, depending a bit on the positioning of the robot inside the pipe, the diameter of the pipe. Then you can measure the basically the distance from the between the internal wall and the system, with a repeatability of 100 microns with this system. You can go lower if needed. In this case, it was enough. And then you have the camera. These systems are synchronized together. So you might have noticed in the previous slides that they are physically not looking at the same location. They are in a configuration 90 degrees, one from the others. But at the end, there is a software that synchronizes everything, images and laser profiles, laser clouds, in order to give one output. Of course, you need some mechanical parts. I will not focus that much on this. This is the rotational drive system, which was part of this unit. Maybe I will try. I hope it works. Yes. So that's a bit in operation. This is what we've done for the development and the qualification. So it's not only the robot itself, the test, the results, but you also have, it was during the pandemic, as you see. You also have to build and have the mock-ups. So this is scale 1:1. So big pipes, big mock-ups like this to test of all possible configurations, and also representative materials. So the material has to be the same of what you will have to go in you will have to test in the power plant. In the this is the type of analysis that this module was able to do here on the right side. So the module, this is a live view. You have the images here. You can have 1 or 2 images depending on the camera that you have. And then you have the profiles of the weld. And here you can do a lot of, and then also what we call radiographic view of the full weld. At the end, what you need to estimate is, okay, how much was the welding, was it okay or not? Do you have any lack of penetration before? And then after you grind it, you also have to estimate how much material has been removed. That was a bit the one of the requirements for the module. So here, that's a big project, a lot of development, a lot of qualification, not only for the mechanical part, also for the software. You need to prove that the software also is reliable. And then in this case, it was also, we decided also to go together with our partner for automatic reporting. So the report is automatically generated at the end of each inspection. Voila, so that's a bit more an example of a big project. And then I will go to a different topic. This is the inspection of the Venturi pipe in a nuclear power plant, but it's a secondary circuit. In this case, we are not talking about contaminated pipe. The environment is not radiating, you can stay there. But the pipe is something like this. So it's a Venturi system. I will put the requirements and then I will explain. In reality, the Venturi is this convergent divergent pipe, which is a pipe inside another pipe. So if you want to access it, and then you have some tubes around it, it's used as a flow meter. You need to, with this device, you can measure the flow, and then with the flow and pressure controls, you know, you have an idea of the power which is produced by the reactor. So the problem in this case was that there was a drift of pressure, which was causing, you can actually regulate a bit the power and the flux in such a way to solve the issue. But of course, during the shutdown, we were asked, okay, what's the cause? They were thinking about possible erosion. If you have erosion in this area, then the flux changes and then you have a drift, possible drift, or any leakages that could happen. Yeah, in this case, we are talking about also problems. We had some requirements on the insertion point. It was a valve, very small, 208 millimeters. Then the pipe went up to 400 millimeters. The pipe of the Venturi is not a cylindrical pipe, it's a convergent divergent pipe, so the manipulation was a bit more tricky. And then we wanted to evaluate the possible erosion compared to the CAD using a laser scanning profilometry with the resolution more or less of 500 microns. The problem again here with the CAD comparison is that, okay, the CAD is the CAD, the as-built is something different. So you will probably see later on. So again, this was a teleoperated, but in this case, the fact of having a robot teleoperated remotely was not given by the need of any contamination of radiation. We could stand there close to the Venturi, but this is how the Venturi looks like. It's a pipe. Inside this pipe, there is the Venturi, and if you want to dismount everything and change it, it costs more or less €1 million. So, okay, there is only one area that we try to inspect from the outside with ultrasonic, but at the end we were not able to have all the required information. So the Venturi is there more or less, 6 meters in length. There was also another very important constraint. We were contacted at the end of January, and we knew that the robot and inspection had to happen at the end of October. So this was non-negotiable. So timing. So when you have something like this, you make a plan, 5 months for development, then you need to do some tests, of course, 3 months for 3 months for the production, and then some tests before going on site. Again, here the phase is how we work, more or less the same approach, but of course, in this case, there was no need for qualification, also no time for qualification. And we did the inspection. I did it in this case, so no training. But the conception phase and the development, since the time frame was very short, we started from something which was already existing, from experience that we had already, modified it, make it also, I would say, not fully robotized, you will see it, but almost completely robotized. So there were some parts which were robotized, some other parts which were in a push-pull system configuration. So, and we came up with something like this. Basically, it's the same module that you've seen before for the big project on the primary circuit, but reduced in a small size. Here we are talking about diameters 200 millimeters. Which is also demountable because you need to insert it inside a valve so the parts can be removed and then you can mount it once it's included in the pipe. So that's a bit the development that we did. This is the robot. Then we did all the test of the different configurations. So you see that you can remove only the front part, insert it in the valve. Then once in, you put the wheel system in, and then it can circulate inside the system for 6 meters till the point of the inspection. The test, it was a very pragmatic approach. In this case, we did not have the requirements to prove on the same material, so we 3D printed the mock-up. This is 3D printed in polymer with the different you see sections that could be mounted one with the other. The most critical section is, of course, this one, the Venturi mid section, because that's the point where you can have erosion. So we did the test here, and then we did the inspection of the full Venturi. But, of course, with the comparison with the CAD, but the main number that we were interested, it's this one, because it's the mid section which is driving the drift. And there was 330 microns of difference with the CAD, which does mean that it's actually a real difference because the as-built could be different. In any case, even 4 millimeters in the mid section would not have explained the problem. So we were far from saying, so the conclusion, you can also have from the system a full 3D visualization. Here you might not see very well on the screen. This is a combination of laser points and images, which are stitched together in one single output. And then you have the difference. So the cause in this case was something else, which we were able to detect, but it was not due to erosion. So it was an additional inspection that we had to do, and we found the cause. It was a leakage somewhere, but no erosion. So I made a brief summary of, okay, why we use robots in the nuclear. Of course, if it's contaminated area, highly irradiating area, high dose, then you cannot enter the area. You need a robot. It's to decrease the risk that the operator takes. It's also the possibility of having digital data, high reliable data, high accuracy and precision. The robot is able to give a precision in terms of positioning of plus minus 1 millimeter, and the repeatability of the laser of 100 microns. So these are very reliable and precise measurements. And of course, as you've seen it here, I have only shown 2 techniques, laser profilometry with visual inspection combined, but there is the possibility to combine multiple technologies like ultrasonic or any other type of NDT testing in a single unit, and then to combine the data together. So make it faster, reliable, and of course less risky for the people working in the power plant. That's it from my side. If you have questions, I'll try to answer.
Okay, thank you.
Many thanks, Alfredo. That was really interesting. And I would have 2 quick questions. The first one would be, how many operational deployments have you had so far? And I'm especially thinking about the first deployment that you showed. There is quite a bit of work with the mock-up and everything, but I assume that once it's done, well, you can really replicate it a lot.
Yes, there we don't do the inspection. For the first one, we train the operators. Then we are only available if there is a problem, technical problem, remotely or even on site, but we are not doing the inspection ourselves. So, And then in that case, it's not a single robot. I think it was 2 or 3 robots for a parallel inspection on different sites. Okay. For the Venturi, I did 1 inspection. There is interest in doing other inspections in Europe, but for the moment, this one was the first type of inspection ever done on the Venturi in the world with this technology. So before it was not inspected.
And would you see this becoming kind of a standard procedure as part of the decennial review of, decadal review of these plants?
Well, it depends. It depends on the country. It depends on the material used for the Venturi. In some countries, I will give you the example of Belgium because I don't want to give you other countries' examples. But in Belgium, probably not, because we know that the material is not prone to erosion. We do also the material testing. But in any case, if you have a drift, you will check it, yes, but it's less likely to have an erosion causing the drift. In other countries, because of some different choices of materials, then we know that the Venturi can actually be completely perforated. You can lose 9 millimeters of thickness. It's possible, yes. The problem is not the Venturi itself. It's that when you have erosion, you have these components will go to the this is the water that goes back to the steam generator, and that's the problem. You won't have you don't want to have material back in the steam generator. It might be that it will be a requirement for some countries.
Okay, and then, sorry, very quickly, my second question, speaking about the requirements. So you mentioned that for the first case in the primary circuit, the requirement booklet was quite thick.
Well, when you work on that's a bit also the discussion we had at the beginning today, it depends a lot where you have to intervene. Yeah. If you intervene on the reactor or on the primary circuit, then the amount of test, even administration qualification, it's consistent. I cannot say that differently, because indeed you need to prove that you are not causing and you will never cause any harm to the primary circuit. And there you need to do a lot of tests. You need to fulfill a lot of, you need to look at the different codes, because some countries have different codes. Belgium is using the ASME code, the American standard. Yeah. In France, there is the RCCP code. You go somewhere else, there is another code. So first of all, you need to check what is the requirement from the code, and then you need to fulfill a lot of qualification tests. To have a robot qualified for this, it's quite a challenge. And so to give you an idea, I was involved for one module, the profilometry module, more or less for 4 months of testing. And then you need to prepare a report with the full results of the testing, so only to qualify the system.
And so now to my question, and then I'm done. But a lot of innovators coming to the nuclear sector complain about this. Yeah. And personally, I'm a bit conflicted, because at the same time, I like these power plants to be really safe. So what is your personal take on this? Is it too much, or
the qualification? You mean?
Well, the whole burden of all these requirements and
well, as I said, the requirements are not huge if you work not on in the technical area, even on secondary circuit, even it's not the same type of requirements, not the same type of work. Here you see in the second example, we didn't have to do any qualification. It was an expertise mode done. In that case, you need just to prove that, okay, there are some things that you can do. Remove the robot from the pipe. It's the first thing that they will ask in this case. But for the rest, it will be less complicated. On the qualification and the intervention for the primary circuit, the reactor, I believe that the qualification is needed. Also the qualification, not only of the material, the robot, also the personnel has to be qualified. We as NDT inspector, we need to be qualified to do the inspection. So that's also part of the safety, nuclear safety first, and for this type of activity, I think it's relevant.
Thank you. Maybe one last question, if any. If not, I will give the microphone to our chairman to close the session, if you like.
Thank you.
Well, thank you again, Alfredo. That was really interesting. And for the rest, yes, so I would like to thank everyone for joining us today, both physically and online. Thanks again to our speakers, of course, who shed some light on the challenges and opportunities to come for robotics in the nuclear sector. And thank, of course, then the Brussels Institute of Advanced Studies, Emanuele and Anya in particular, for organizing this session and inviting us to invite a few speakers. Without further ado, we can go perhaps to see, for those who are interested, the Nimbl'bot robot very quickly before Ludovic has to leave, and take a last cup of coffee while discussing robotics. Thank you very much, everyone. Thank you.
Okay. The robot can move along a curve we have defined with the head of the robot. I will go back just to restart the movement. At the moment, all the system, the black tubes and carbon tubes and the robots weighs 5 kilograms. That means it can be easily placed on a rover, on something else, to be introduced in a confined area. And the way to control it is just to change the orientation of the head of the robot. Now it's straight. I will move the head and I will push the robot and it will follow, it will go up. I increase the curvature and the robot will follow the curvature I've done with the head. Now with just one, I will go straight now. And with the camera, we have a feedback of the environment we can see. The obstacles are too far. The distance of vision of the camera is less than 5 meters. That means we cannot see very far. Okay. Is someone want to test? Okay. We can break everything, but yes, yes, of course. Just this button to go back, go front.
Okay, why is it moving?
Because it's straight. The head is straight, but we are in the singularity. If you change the orientation of the head, up, now it is stabilized.
This is
okay, and then if backwards, yes, in the opposite button will go.
No, this way.
Yes, what? And yes, where you want to go?
I don't know. I'm just pressing and seeing.
Yes, this one. Yeah? You go outside.
What if it will fall out?
It will follow the orientation of the head of the robot.
Okay, but it cannot fall out. More?
Yes, yes, okay. yeah. Yes, the robot move and go out now.
And I can rotate the head?
Yes, this one.
No. Okay, nice.
Thank you.